You build an autonomous agent. In a static testing environment, the logic holds up, but the moment you deploy that agent into the live, dynamic conditions of production, the system breaks down. These breakdowns manifest as three specific structural system failures: oscillation, overload, or freezing. Typical engineering attempts to solve these as isolated logic bugs. We open the system prompt and add natural language instructions, telling the model to think carefully or stop repeating itself, attempting to patch a structural deficit with better phrasing. These production failures are deterministic system dynamics failures. Resolving them requires mapping environmental variables to the LLM's API parameters using the rpcs1 cognitive systems framework. Stabilizing production agents requires a transition from trial-and-error prompt engineering to a rigorous mathematical calibration of receiver parameters. The rpcs1 framework translates abstract environmental conditions into exact parameter values across 5 cognitive receiver primitives. The first is temporal integration, or TI, controlling context window strategy and maximum token limits. Signal gain, or SG, dictates how strongly the agent amplifies data, mapping inversely to temperature. Filtering threshold, or FT, determines how conservatively the model gates actions, driving tool use strategy. Update elasticity, or UE, measures readiness to revise internal assumptions, setting the foundation for retries. Finally, ambiguity resolution, or AR, defines commitment aggression in highly uncertain environments. Once these 5 primitives are configured, they form a deterministic control layer that dictates agent behavior, effectively overriding raw reasoning errors. The first failure mode, oscillation, is characterized by an agent refusing to commit and looping through identical tool calls without executing a final action. This occurs when high signal gain and high temporal integration are deployed into a fast-changing environment. This can be diagnosed using the core axiom of the rpcs1 framework, the matching principle. It states that optimal temporal integration, TI, must be inversely proportional to the environment's entropy, or rate of change, H. In highly dynamic environments, new variables constantly overwrite old ones. Maintaining a large context window forces the agent to reconcile incoming signals with conflicting, outdated data, causing execution gridlock. To fix an oscillating agent, we drastically shorten the context window to match the high entropy and lower the signal gain. Disregarding the entropy rate of the deployment environment leads directly to oscillating behavior, regardless of the underlying LLM scale or training. The overload failure mode occurs when an agent bypasses its standard execution paths and generates hallucinated tool